Okay, we're going to start a really interesting unit. This is the first section. This is 10.1. The I can statement is I can understand the basic concepts and vocabulary. So write the word vocabulary right here of probability. Of probability. So the warm-up question here basically just says lists three things that you already know about probability. You may have heard something about this in a previous class, or maybe just in as you've been talking with friends about the chances that something would happen. Whenever we're dealing with probability, you may know that there's some chance involved. There's probably some uncertainty about what's going to happen. And maybe there's some random outcome or different things like that. And we're going to talk about some of those words. So anything that you already know about probability right now is just kind of bonus. So today what we're going to do is we're going to talk about and discover some of the basic concepts and vocabulary dealing with probability. And we're going to start with a simple group experiment. Now, since I'm recording this video, I'm going to use some data that I collected with a class that I taught last year. But here's the basic idea. Everybody's going to get a coin, and we're going to record the outcome of flipping that coin. Okay, so the outcome is the result. The outcome is the result of a probability experiment. So we're going to be flipping a coin, and we don't know the outcome, so we're going to call that a probability experiment. And whatever it lands on, head or tails, that's what the outcome is going to be. So the outcome is the result of a probability experiment. So here's what we're going to do. We're going to flip the coin 10 times, and we're going to tally the results in this table, and then we're going to wait for further instructions. So as you go through and flip a coin, and if you want to follow along and pause it, that would be just fine. So here's what you're going to do. Maybe you get a head, then another head, then a tail, and then another tail, and a tail, and maybe a head, and a tail, and a head, and another head, and a head, and then that's it. So I'm going to kind of just reproduce the results that I had before. So the tally right here, the heads tally up to 6, the tails tally up to 4, and the total was 10. So I conducted that experiment, that probability experiment. I flipped the coin 10 times and I recorded the results there. Now I'm going to summarize what happened in a class, and this is the number of heads. So I'm going to put an H right here, and I'm going to put a 0 underneath this, a 1, a 2, a 3, a 4, a 5, a 6, 7, 8, 9, and a 10. And what I'd do is I would survey the class and say, okay, raise your hand if you had 0 heads, or 1 head, or 2 heads, or 3 heads, or so forth. Because remember, if you got all tails, you got no heads, and if you got all heads, you got 10 heads. So let me just track the results here. So in this particular class, here's what happened. There was 1 person that had 2 heads, 6 people that had 3, 8 people that had 4, 7 people that had 5, 8 people that had 6, 2 people that had 7, 1 person that had 8, and nobody had 9, and nobody had 10, and nobody had 0, and nobody had 1. So this is how things worked out. We could count these up and see how many students were in this particular class, but nobody got a 0 or a 1 as they were flipping through and counting up the numbers heads, and nobody got a 9 heads or 10 heads. Okay. So then what we'll do is we'll kind of enhance this experiment, and instead of doing it 10 times, we're going to do it 50 times. Okay, so you could either do it another full 50 times, flip a coin 50 times, or you could just do 40 more. I would really encourage you to go ahead and do 50 more times. So if you went ahead and did that experiment, go ahead and pause the video and flip it 50 times and then tally your results and see if it falls in line with what we've got. So you can pause it right now. I'm going to show you the results that I got. Okay, we're back. Here are the results of me flipping a coin 50 times. We ended up with 23 heads, and if you count those up, that means 27 tails, so the total was 50. And then I did the same thing. I'd survey the class, and if you did this, you could kind of see where your results turn out here. So we're going to keep track again of the number of heads, and then this is going to be 0 to 5 heads, 6 to 10 heads, 11 to 15, 16 to 20 heads, 21 to 25, and so forth, all the way up to 46 to 50 heads. So as we go through here, here's what ended up happening. No one was in this category. 1 person had somewhere between 6 and 10 heads. In this particular class, no one was in the 11 to 15 category. From 16 to 20, there were 5 people that had somewhere between 16 and 20. 12 people had between 21 and 25. 11 people had between 26 and 30. One person had between 31 and 35. One person had between 36 and 40, and nobody had more than 40 or 41 or above. So here are the results, and kind of think about where yours kind of turned out. If you did this, you probably ended up somewhere in this range right here. And then I also want you to take a look at kind of how these are distributed. There were a couple people that were way out toward the end here, but most of them were kind of bunched in here, and even more so right here. Most people were between 21 and 30 heads. Now let's talk about exactly what probability is, because we just kind of did a probability experiment, tracked the results. So probability is this. Probability is the measure of the likelihood of a random outcome. Now we know what the outcome is. The outcome is a result. Okay, random means a couple of different words would be good here. So random means unpredictable. You could also say something like maybe uncertain. That would be okay too. So either of those words would be just fine for random. A lot of times we use the word random in ways that maybe aren't intended, or maybe in ways that don't apply to probability. But when we talk about randomness in probability, what we're talking about is things that are unpredictable or uncertain. Okay? And basically what it is the long-term ratio with which an outcome will occur in situations with short-term uncertainty. Now we're going to talk more about that in just a second, but if they are a long-term ratio, then probabilities are flat out, they are ratios, they are fractions. So they can be expressed as fractions. They can also be expressed as decimals, and they can sometimes be expressed as percents. Now, I put a little asterisk by this one because most of the time we're going to talk about probabilities in terms of fractions. Occasionally we'll use decimals and percents, but most of the time we're going to talk about them as fractions because they are ratios. They're a comparison of a number on the top and a number on the bottom. So as an example, let's talk about how this vocabulary would apply to flipping a coin. If we flip a coin just once, okay, that's a short-term outcome. We're going to flip it just once and we're going to figure out what the result is. And we can't really predict whether it's going to be a head or tails. However, we do know that if we flip the coin many, many, many times, we do this over and over and over again, or do it in the long term, so we make a long-term process out of this, what's going to happen is we're going to end up with roughly half heads and roughly half tails. Because there's two sides, they both would happen kind of equally likely, so we would expect it to be roughly half heads and roughly half tails. So let's come back up here and take a look at this right here. When I did this, I ended up with 6 heads and 4 tails, so roughly half and half. When I did it here, I ended up with 23 heads and 27 tails. 25 would have been split right down the middle, but that's pretty darn close. That just kind of shows that uncertainty or that randomness or that unpredictability when we do a probability experiment. And then if we look at the students in this particular class, notice how many of them were in this range here between 4, 5, and 6, so right about halfway. And then same thing down here. Halfway would be 25, so we'd be right about here. That's what happened with most of the outcomes. And again, it's not a predictable thing. It's not that we can say for absolute certain what the result is going to be. It's not always going to be 50-50. Half and half, but most of the time it's going to be somewhere close to that. So what we'd say right here is we would say the probability of heads, and that's the notation that we use. So we use a P to represent the word probability. This is just kind of a shorthand that we typically use. Probability. So if we say P and then a set of parentheses, what we mean is the probability of getting a heads. That's going to be about 1/2. And then the probability of getting a tail, that's also going to be about 1/2. So if we want to look at this a little bit further, we need to have some more vocabulary. So let's kind of expand on this. We're going to talk about something called a sample space. and we're going to use this quite a bit. We use a big capital S to represent the sample space, and it is the collection of all possible outcomes. So all the results that can possibly happen. So the sample space for flipping a coin is just a list of all the things that can happen. And what can happen is we can get a head or we can get a tail, and that's it. Now you might say, well, gosh, it might land on its edge or something like that. And in reality, that just doesn't happen. And if it does, it hardly ever happens. It's almost impossible, and we'll talk more about that in just a second. So an event, which we use a capital E for that, is the specific desired outcome, or we could say result, from a probability. So the event, we could say, well, we wanted heads. That's what we defined up above. We said the event that we want to keep track of is the event of getting a head. Okay, so landing on a head or landing on a tail would be the two specific events that we could be talking about. And then equally likely is what we say when each event has the same probability of occurring. Same probability of occurring. Or we could say the same chance of occurring. We could use that word also. So if they're equally likely, they have the same probability, or they have the same chance of occurring. And that's what happened with our probability experiment with flipping a coin. So the probability of getting a head was 1/2, and the probability of getting a tail was 1/2. So those have an equal chance of happening. Okay, now when we talk about probability, we want to make sure that we understand some very basic rules, some really important rules, and these are some very, very strict rules about probability. So let's talk about what these two rules are. The first rule is that the probability of an event, so the probability of some event, P of E we say sometimes, will always be greater than or equal to 0, so it's always going to be bigger than or equal to 0, or less than or equal to 1. And the second thing is the sum of the probabilities of all the possible outcomes, so all the possibilities, if we add all those up together, then it has to equal 1. Now, if we know those two rules, then we can make what we call a probability model. And here's how we make a probability model. We list all the possible outcomes. We list every single one of the outcomes of a probability experiment. We list each outcome's probability. Outcome's probability. And then we want to check something. We want to make sure that this probability model satisfies rules 1 and 2. So in other words, it can't be negative, can't be bigger than 1, and they have to add up to be equal to 1. Okay, so we want to check that every time. So what we're going to do here is we're going to make a probability model to show how these rules apply for our coin flipping experiment. So here's what we want to do. We want to list all the possible outcomes. So we're going to list head and tails. Okay, so head and tail, those are the two outcomes. The probability of head is 1/2, the probability of tail is 1/2. And then let's check. Have we listed all the outcomes? We have. Did we list their probabilities? We have. And then we want to make sure, do these obey rules 1 and 2 for probability? So do we have any negatives? We don't. Do we have any probabilities that are bigger than 1? We don't. And do they add up to 1? If we add 1/2 and 1/2 together, we end up with 1. So that works great there. That is a perfectly valid probability model. Now let's talk about that thing we were talking about earlier. Is it possible for a coin to land on its side, on its edge? Well, that's pretty much impossible. So if we have an impossible event, it has a probability of 0. The number that we would use, or the ratio that we would use to represent that probability, is 0. So in other words, there's no way it would happen, or we could say fat chance it would happen, something like that. Okay? Now, if it's what we call a certainty event, that means it's absolutely certain to happen. Well, that has a probability of 1, or in other words, 100%. So it's a sure thing. It's absolutely guaranteed, something like that. Now, if we have something that's unusual or uncommon, if it's unusual, if it doesn't happen very much, it would have a low probability, so something closer towards 0. If it's a very common thing, then it would have a very high probability. So it's going to be something probably more than 1/2, something closer to 1, okay? Now, we're going to use this word quite a bit throughout the unit here. So we're going to talk about frequency. Frequency is just a fancy way of saying how many times an event has occurred. How many times an event has occurred, okay? In other words, it's kind of like the tally. If we count up how many times something happened, that's what we're talking about when we say the frequency. Okay, let's flip the page over and let's talk about a little bit more vocabulary. Now, if you're worried about the homework for this section, most of the homework for this section is just kind of making sure that you're aware of the vocabulary. So don't worry about soaking all of this in at once. I'm going to give you an opportunity to make sure that you've got this figured out. So on the second page, let's talk about experimental probability. So, a probability experiment is conducted, so like flipping a coin, rolling a die, or something like that, and the outcomes are recorded. The experimental probability of an event, so in other words, the probability of that event, is the frequency of the event divided by the number of, and we use this word, the number of trials. So how many times did this occur, whatever that event happened to be, divided by the number of trials, or how many times we did that. Now, in order to figure out what the experimental probability is, we've got to conduct the experiment many times in order to get a good estimate of the event's probability. Okay, so the experimental probability is figured out this way. It's the frequency of E, in other words, how many times did it occur, divided by the number of trials. Now, sometimes what I'll say is it's the tally over the trials, if you want to remember it that way. So when we're talking about an experimental probability, we tally up how many times whatever it was, we were interested in counting, divide it by the number of trials, and that's the experimental probability. So one star here says, what is the experimental probability based on our coin flipping for the probability of heads? So if we come back here, now I'm going to use the one that I did. It's this one right here. So if we were to compute the experimental probability of getting ahead on this one, the tally for heads was 6, the number of trials was 10, so we'd do 6 out of 10, and we'd write that down for our experimental probability. So we're going to do 6 over 10. Now stop and think, what could we do to make that more accurate? Well, to make that more accurate, we could do lots and lots and lots of trials. So to make it more accurate, we're just going to say we could do more trials. The more trials we do, we make it a longer term experiment. We do a bunch of trials and track that. That's going to make it more accurate. Just like when we went from 10 trials of flipping the coin to 50 trials of flipping the coin, if we did 1,000 trials of flipping the coin or something like that. Okay, now, because we compute the probability relative to the number of trials, so relative to the number of trials, this is also called the relative frequency. More vocabulary there. So if somebody says the relative frequency, what they're talking about is they're talking about the experimental probability, or they're talking about the tally over the trials. How many times did that event occur? What was its frequency divided by how many times we did that? Now, I've got a red asterisk by this because it's an important concept. We're going to talk about that throughout the unit, so don't worry, you'll have time to get the details. And then I've got one next to this one, and then the next topic called theoretical probability. But I want to make sure that you catch this one right here, so I'm going to put an extra asterisk right there. Okay, we try not to use experimental probability unless we have to. Okay, we're only going to use experimental probability when we're trying to establish probabilities, or when we're trying to verify what we're going to call theoretical probabilities, and we'll talk about that next. Now, I'm hoping you've heard of the game called Pass the Pigs. Pass the Pigs is a really fun game. It does involve probability, and let me show you what it looks like. When you play Pass the Pigs, it's kind of like rolling dice and stuff like that. Only the dice are shaped like pigs, and they look like this. Now, if you throw these onto a table, they can land in lots of different ways. We've got this one that's standing on all 4 legs. We've got this one that's on its 2 front legs and then its snout. It's really hard to figure out how they're going to land. So we would need experimental probabilities for this, because actually figuring out all the different ways that it can happen, it's not equally likely what's going to happen. So what most of the time happens is it ends up on its side, and that's called a sider. Sometimes it'll land on all 4 feet. That's called a trotter. And then sometimes it'll land on its back. They call that a razorback. You'll notice that this one is only worth 1 point if you roll it because it happens quite a bit. These happen a little bit more often, but they're worth 5 points. And then some things that don't happen very often are things like a snouter, like landing on its 2 front feet and then on its snout. That's quite a bit. And if you get a double, that's 40 points. And then something called a leaning jowler. And a leaning jowler is where the pig actually is on one of its hooves, a snout, and then on an ear. Doesn't happen very often, which is why it's worth so much. Okay, and on this one, if they happen to touch each other when they land, that's called an oinker, and you don't get any points for that. Now, there are actually people that have passed these pigs, thrown these pigs on tables hundreds of thousands of times. They've tallied those up, and that's how they came up with the kind of the point assignment for the game. So the only way to really establish what the probabilities are for passing the pigs and how they're going to land and different things like that is to actually roll them. They're not uniform figures, they're not shaped nicely or anything like that. So you'd actually have to use experimental probability. You actually have to do a bunch of trials in order to figure out those probabilities. Okay, but that's an example of where we'd have to use experimental probability because there's no good way to figure out what the probabilities are otherwise. Now, most of the time we're going to do this. We're going to do something called theoretical probabilities. So with theoretical probabilities, we do not need to conduct an experiment. Instead, the way we figure out the likelihood of the probability of an event, it's just based on all the possible outcomes. And usually they're equally likely, so each one has an equal chance of occurring, like we talked about with flipping a coin or rolling a die or something like that. So the theoretical probability is really easy to compute. It's equal to the number of ways the event can occur, and then we divide that by, remember we talked about these always being ratios, we divide that by the total possible outcomes. So if we're doing theoretical probability, it's the number of ways E can occur, how many ways that event can happen, divided by the total possible outcomes. Now, we can actually use this to verify what the theoretical probability, what we expect to have happen when we flip a coin. So when we flip a coin, there's one way that a head can occur, and there are 2 different outcomes, head or tails. So one of them is a head, but there are 2 outcomes altogether. One of them is a tail, 2 outcomes altogether. Now, one way you can describe the difference between experimental and theoretical probability, and we'll talk about this more in a later section, is experimental probabilities are what actually happens when you do the experiment. Theoretical probabilities are what you expect to have happen. So we're going to come down here, and I'm going to show you how you can do probabilities, experiments, and simulate probabilities like rolling a die or flipping a coin or something like that on the calculator. So in order to do that, let me just show you really quickly what we're going to use. We're going to use the PRB button, that stands for probability, where that's going to allow us to access the probability menu. And then we're going to hit something called RANDI, that stands for random integer. So we're going to bring that up. We're also going to need the comma key and then the parentheses key. So I'm going to go ahead and bring up the calculator, and I'm going to show you how these commands work. And we're actually going to simulate flipping a coin. Okay, as you can see, I've got the calculator all set up and on the screen. And you can see the screen here, and then you can see the PRB button, the probability button right there. So here's what we're going to do. We are going to type this in. So we're going to hit the probability button, and you'll notice that a menu comes up, and you can either do the right or the left arrow. If you do the right arrow, it takes a little longer to get there. So that's the one that we want. We want the RANDI. I'm going to go back to the home screen. I'm going to hit probability again. It's a little quicker to get there if you hit the left arrow. So we're going to hit that, and it's going to do RANDI. And again, that stands for random integer. So it's going to give us an integer that's just randomly generated, and we have to tell it this. So here's the syntax. We pull up that RANDI, random integer, and then we do the lower limit, the smallest integer that we want the calculator to produce. And the upper limit, and we need a comma in between those. So you'll notice that it already has a set of open parentheses right here. So if we want to simulate flipping a coin, there are only two outcomes. So what we're going to do is we're going to say random integer. We're going to hit a 1. Then we're going to hit a comma. Again, the comma is above the close parentheses key. So we're going to have to hit the second button because that's in blue. It's above there. There's a comma. And then we put a 2, and then we close the parentheses. So what this is going to do is it's going to produce a random integer between 1 and 2. Sometimes it'll give a 1, sometimes it'll give a 2, and that can be used to do what we call simulate flipping a coin. So when I did this experiment in class, and when I did it, whenever I do something like this, I actually don't flip a coin. I actually have the calculator simulate these probabilities, or simulate rolling flipping a coin by doing this right here. So let me show you what happens here when I hit enter. When I hit enter, it gives me a 2. So what I do is I would tally. A 2 is a tail, so I'd tally a tail. And then I don't have to type in that whole command again. What I can do is I can just hit enter, and then it gives me a 1. Now I'm going to keep hitting enter, and every time you see that change, so it gives me a 1, it gave me another 1, another 1, a 2, a 1, a 2, a 1, a 2, a 1, a 1, a 2, a 2, a 2. So it will just keep generating those random integers between 1 and 2. So if you did that 10 times, so let me clear this off again, and I'm going to just type that command in from the start. I'm going to hit probability. The quickest way to get there is to hit the left arrow. I'm going to hit enter. That will bring that back to the home screen. And if we want to simulate two equally likely outcomes like flipping a coin, I'm going to hit 1. That's going to stand for the heads. And then I need to get the comma right there. It's above the close parenthesis key. So I'm going to hit second, hit the comma, tell it how high I want to go. I want to go up to 2. I'm going to close the parentheses. Now if I want to do it 10 times, here's what I'd do. I'd hit it once, tally a 1. That would be a head. Hit it again, tally a 2. That would be a head. Another 2, sorry, that would have been a tail. Another 2 is another tail, another tail, another tail. Wow, 5 tails so far. Now we're back to a head, another tail, so we're at 6 tails, 7 tails, and then there's 3, that would be 3 heads. So we would have gotten, in that experiment, we would have gotten 3 heads, 7 tails, and that's the way that works. So if this will allow us to simulate two equally likely outcomes, this random integer parentheses 1 comma 2, can you think about how you could simulate flipping a 6-sided or rolling a 6-sided die? So if there are 6 sides, they're all equally likely. So think about what we do here. So we would do rand I, and then we're going to do parentheses. A 1 would represent a 1. Now we don't have to put all of them in between. It's just the smallest one we want and then the biggest one we want. So again, I'm going to clear this off. I'm going to type this in again. Probability, hit the left arrow, bring up rand I, random integer, 1, comma, all the way up to 6. Now if we do this again and kind of simulate this experiment, let's say we roll a die 10 times. So it gave me a 3 the first time, then a 2, then a 4, then a 5, then a 2, then a 1, then a 6, and we just keep track of how many there are and tally those up. And that's actually what I'd like to do right now. If we've got time in class, we'll go ahead and start this in class. You do need a calculator that does this type of thing, so I hope you've got one of these TI-30 XII, either an S or a B, the S or solar ones. So here's what we do. Make an experimental probability model for a fair 6-sided die. So what that means is it's equally likely to land on any one of the 6 sides. And we're going to roll it 100 times, tally the results in the table, and then compute the experimental probability. So the possible outcomes are 1, 2, 3, 4, 5, and 6. Not quite sure why there's an extra one there. I'll get rid of that for the handouts. And then we do the tallies right here. So the tally is going to be the frequency. So we're going to tally those up, and then we compute the experimental probability. Now I'm going to give you time to do that. I'm going to stop the video in just a second, but what I'd like you to keep in mind is this. Here's all you need to do. This is the assignment for section 10.1. Finish example 2. So I want you to go ahead and finish this and actually compute those experimental probabilities. So those ratios, you know, the tally over the the trials. So each one of these would be over 100. And then I want you to read the front and the back of these notes at least twice. Again, it's the familiarity with the vocabulary that's really going to help you out here. So it's not a huge assignment. I just want you to read this at least twice, and then I want you to be ready for a quiz on the vocabulary and some of these concepts. So if you've read through this and done this experimental probability that we're talking about right here, finished up that experiment, read it a couple times, you should be in good shape for the quiz tomorrow. So I'm gonna, if you'd like, go ahead and pause the video. I'm gonna show you what some of these results would look like if you did them. So I'm gonna actually conduct the experiment and then show you the results. Okay, so here's what happened. The frequency when I did this experiment, I ended up with 14 ones, I ended up with 19 twos, 15 threes, 10 fours, 19 fives, and 23 sixes. So if we compute that experimental probability, every one of these, the tally is 14, the number of trials is 100. So this would be 14 100ths, 19 100ths, 15 100ths. We won't worry about reducing anything for the time being. We'll just write down each one of these and go from there. If you've done that experiment yourself, that'll be great. I do want to show you one other thing that we'll talk about, and that's this. I actually went through and had an entire class of about 36 students. They did this, and each one of them did it 100 times. So this was 3,600 trials. And we counted up how many ones we had out of those 3,600, how many twos, how many threes, and so forth. And here's what we ended up with. We ended up with about 17.8% of them were ones, about 17% twos, and then 16.1 threes, and then so forth. You can see those numbers right here. What I'd like you to notice is this is an experimental probability. These are not all going to be the same. But I'd also like you to think back, well, if there are 6 outcomes, so this is experimental, and if we did this theoretical, let's see, theoretical, there we go. Well, say we want threes. Well, there's one way to get a 3, and there are 6 different outcomes. Think about what 1/6 would be as a fraction, or sorry, as a decimal. It ends up being 0.1666 and so forth. So if you move it over 2 places, it'd be 16.6%, and look how close those are to 16%. So theoretical probability is the way things are expected to turn out. That's what we think will happen. And then the experimental probabilities, these guys right here, that's what actually happened when we rolled the die 3,600 times. Okay, again, read through the notes a couple of times, finish this experiment right here, do your 100 tallies. It should be pretty quick with the calculator. And then make sure you're ready for that quiz.